Record. So we're gonna do more real analysis, diving into the deep, I think. Metrics, absolute value, topology. I'm not really focusing on topology in R because it's kind of, well, maybe I should talk about it briefly. So if you have a real number line, we can talk about like a few different things. So we could talk about like, say this is 0. We might talk about like the rate or the interval -1 to +1, which is like here, right? This is like -1, this is +1. Yeah, so you can think about that interval. And that's like sort of like, there's a couple ways to think about it. You could think about it as an interval, but I think like one of the things that I want to get across in terms of topology is that this is a circle, and it doesn't look like a circle, but it's a circle. It's like a disk. So if you think about drawing a circle of radius 1 around the origin, it's a bad circle. That's a terrible circle, but you get the idea, right? It would pass through that -1 and it would pass through that +1. So really, if we don't care about like complex numbers, which is like everything up and down, the circle of radius 1 centered at 0 is the interval from -1 to +1, right? Does that make sense? It's a little weird, but like that's like if you think like a circle is like a 2-dimensional circle, and then like a sphere is like 3 dimensions, right, of that same idea. A interval is like a 1-dimensional circle. It's confusing, but hopefully that makes sense. Metrics are distances, and I think we covered that a little bit in linear algebra. But the idea is that it's a function, takes in like 2 objects. In this case, like we're thinking x and y are real numbers because it's real analysis, but you can define a bunch of different metrics is basically the long and the short of it. And generally speaking, you think of a metric as like the distance between 2 things or how far apart 2 things are. But there's different ways you can conceptualize that, right? So I think in the lectures, Moran talked about different types of distances. One of them was, I think, the Manhattan distance. And I think he talked about, is it like Hamming distances, which is like the distance between like words or like strings, if you want to think of them as that. Yeah. So different kinds of distances. We have absolute values, which is sort of the last thing I want to talk about. Sorry, before I move on, there's a bunch of axioms for distance that I don't remember off the top of my head. But basically it's like distance is non-negative. The distance between x and y is the same as the distance between y and x. They're all kind of like pretty basic things when you think about like actual distance, say in like vectors. But we can abstract that, right? So as long as it meets those sets of, it's a function that meets those sets of rules, then we call it a distance or a metric. Metric is just like the abstract word for distance, right? So like, yeah, so like we can abstract things, and I think at this point you probably should be okay with that-ish. The idea of like having distances that aren't actually distances. We did that in linear algebra too, stuff like that. And then absolute value. So what's the definition of like absolute value? If I say something like the absolute value of x is less than or equal to 1, what does that mean?
The distance from x to the origin is less than or equal to 1.
The distance from x to the origin.
I guess not, if you change the distance.
The distance from x to the origin is less than or equal to 1.
Right. I guess.
Yeah.
It's on the interval -1.
Yeah, yeah, that's right. Yeah. That's usually like the way I would look at it is like x is between positive and -1. So literally in a proof, anytime you see something like that, just turn it into that. Turn it into that form because like the absolute values are hard to deal with, right? How do you deal with an absolute value? Usually the first step is to change it into like one of these interval things. Does that make sense? Cool. Now proofs with absolute values are a little bit weird, or sorry, not absolute values, inequalities are a little bit weird. And I think we'll get into some of that, but sometimes you can do steps that you wouldn't really feel are appropriate. So like, how do I say this? As an example, if I wanted to prove something, like this is very simple, but if I wanted to prove something like 2 plus x squared is greater than or equal to x squared, that's true, and we can just like drop the 2, right, and show that it's equal. So if we add 2 to one side, it has to be bigger, right? And you'll see stuff like that, where like if you just, like perhaps you start with like, in this case, maybe you start with x squared equals x squared, and then if you add 2 to one side, then this side has to be bigger, right, or equal. But that's the kind of stuff, like when you're doing proofs like that, watch for things where you can just drop something off, right, or where you can just like, yeah, do stuff like that. Does that kind of make sense? We'll do an example of it. Maybe I'll do that now. Cool. So this is from Wade, from your textbook. So the positive part of a number, a real number, is defined by that formula. So I have an eraser, but a plus is absolute value of a plus a over 2. And similarly, we have a minus, which is absolute value of a minus a over 2. That gives you the positive and negative part. And I think maybe the big part of this like exercise is just convincing yourself of that. So, you know, maybe try a couple numbers and see what you get, and see that it actually does give you the positive or the negative part of something. And then I want you to prove those 2 statements. So the first one, that a is a plus minus a minus, and the second one is that the absolute value of a is a plus plus a minus. Do them as a proof as best you can, and yeah, I'll give you some time. I'm gonna take a look online maybe. Let's see the chat and see if anything's going on. Oh, it looked like somebody left. No. Distance on real number line. Oh, you're trapped in the void. What? No. Oh, I'm sorry. I think they can't hear me. Can you hear me now? Yeah, you must be able to, because I'm talking. Oh, my video camera's off. Oh, you can't use camera. Okay, got it. You can hear most of the time, but you can't hear me. Okay. Maybe what I'll do next time is like wear earbuds. That might help, and then like just sync them to the thing. Just put an earbud in, that might help. Sorry about that. Can I hear you guys? Like if you unmute, can I hear you? I don't think so. This sucks. Technical issues. Lots of fun. Oh, because it's coming out of the TV. That's weird.
So the A plus and the A minus are definitions we can use in our proof?
They are definitions. Yep, go for it.
luck now?
Oh, yep, that's definitely there. It's almost a bit too loud. Okay, hopefully that's good. Now I can hear you. And you can see my screen, right? Hopefully.
Yeah, I see the screen that you're sharing.
Great.
Is there any way to share the camera directly to the board?
Is there any way to share the camera? That is an excellent question. Possibly if my laptop will turn on. If not, I will post this video right after class. I'm recording the video on my phone. It's still not great.
Do you want to use my laptop to?
No worries, I can just watch that later.
Maybe, yeah, if someone has like a laptop that you're like not really using, just to like show the screen would probably, like show the board would probably be good.
It's in Discord?
No, it is Google Meet.
No, the invite link.
The invite link. Oh, like the Google Meet link?
Yeah.
Yeah, it should be on Discord. It should be. Yeah, you're right. Thank you very much. Let's see if this works. Gotta turn off blur, I think. There we go. And then join.
Yeah.
There we go.
You're there. Well, use mine.
That's not good. There we go.
And then, is my volume down all the way?
Is your volume down all the way?
Probably. Like just hit the sound buttons at the top.
Oh yeah. Do I have to like press function or anything? Or is it just like,
Just press.
okay, cool. Yeah, you're all the way off. Awesome. Thank you. I need to get this laptop fixed really bad. All right, yeah. Hopefully you can see that all now. Sorry about the technical issues. This is not ideal. If you have any questions, Marion, just let me know. I can go over stuff that I said or, you know, I don't care. I was hoping to be able to do this all on my laptop in the other room. Did you guys get it? Pretty easy, right?
Yeah.
Okay, let's take it up. So, and again, practice proper proofreading if you can. So, first proof, we want to show that A is equal to A plus minus A minus. Those are our definitions. I'll leave them up maybe. So A plus, well, let's start by saying let A be a real number, right? So we want to define like our variables, define our domain. We can say something like let A plus and A minus be defined as right there. So then A is equal to, well, I should maybe start with the hard part. So we'll say A plus A minus, is it plus? Minus A minus, the first part, is absolute value of A plus A over 2 minus absolute value of A minus A over 2. We can combine fractions, which gets us 2A over 2, which is just A, right? Also, A plus A minus is absolute value of A plus A over 2 plus absolute value of A minus A over 2, which we can simplify to two absolute values of A over 2, which is just the absolute value of A. Good with that? All right. No questions online, hopefully. If there were, I don't know if I'd figure them out. Okay, next question. Proof using inequalities. So this is a true or false. I want you to figure out if we assume the first inequality there, that -3 is less than or equal to x less than or equal to 2, does that imply the second inequality? So if you assume x is between -3 and 2, can you show that the crazy quadratic one there is true? Or can you find a counterexample and show that it's false?
How would you start this?
Good question. Let's start with, suppose -3 is less than or equal to x is less than or equal to 2.
Would you like assume half, like -3 is greater than 2x?
Here's what I would do. Can we write something like the absolute value of x is less than or equal to something?
2.
Yeah, but can we be more, like, can we get every piece of it, right? Is there like a statement like this that's equivalent to this? So yeah, 2 is true, but, or maybe, yeah, sorry, you're right. I should have phrased it a bit differently. Can we do like this? Can we find an A and B that could fit in there that would cover the entire range? So as an example, maybe if I do this, if I add 0.25 to each side, then I'll get -2.75 is less than or equal to x plus 0.25 is less than or equal to 2.25. So I've shown that x plus 0.25 is less than or equal to, the absolute value of that is less than or equal to 2.25.
Oh, and then do it one more time.
Yeah, well you could pick a different number other than
Well, if you
2.25.
did like 0.5.
Yeah, I think that's the answer. That's why I didn't do that.
Sure.
But yeah, I think if you did 0.5, you would get an absolute value, right? So if you add 0.5 to everything, and maybe I should do this like in the camera. So online can see it.
Sorry, Ben.
Yep.
0.5 works or doesn't?
I think it works. It should work, and we'll go through it. So if you do, so again, first suppose that x is in the range that we care about here, then we can add 0.5 to every term, right? So we'll get -2.5 is less than or equal to x plus 0.5 is less than or equal to 2.5, right? And whenever you see something like that where it's like negative on one side, positive on the other side, that's just absolute value. Right? So that's just absolute value. I think that should give you a start. You should be able to break some of those equations up. On the right side, so we have x squared plus x minus 6 is less than or equal to 6 times this. Can we factor this?
+3, -2.
Yep. Why can I do this? Or can I do this? Because technically when we factor it, right, we're doing like that. Yeah?
It's a property with an absolute value.
Yeah.
You can write down the multiplication like that.
Across products, yeah. So you can do like that. Cool. And that is less than or equal to 6 times this. Okay, well, if we look at this, we have the x minus, or the absolute value x minus 2 piece here is fine. But like these two are the same on both sides. But we have a 6 and an x, absolute value of x plus 3. Can we compare them? Based on the information we know here, right? Can we plug some of that information into this absolute value? Yeah. Does that tell us anything?
Are you able to cancel, or like, cancel out the x minus 2 on both sides?
Are we able to? Well,
Just so it's like absolute of x plus 3.
what if x is equal to 2,
True.
right? That's sort of the only problem there. But you almost don't need to. Like, you can just kind of, with your hands, cover it up and just see, well, we want to know, is it true that x plus 3 is less than or equal to 6? We aren't really canceling, but we're just asking the question, right? You can't divide by x minus 2 on that interval. But is this true? You can plot it. It's one way to do this, right? If it helps visualize it. So I think that absolute value of x plus 3 is going to have a 0 at negative 3. And it'll just be an absolute value going up. Now on the range that it gives us, which is negative 3 to 2, we'll see it's basically a straight line, right? It's just the line x plus 3, right? So we only care about stuff between negative 3 and positive 2. So really the question we're asking here is, if we plug in positive 2, that's going to give us the maximum. Is that always less than 6? If we plugged in 2 to this, we get 5. 5 is smaller than 6. So the biggest that this here can be is 5. We have a 6 here. So this is true.
So if you're doing an actual proof, how would you?
Well, you would basically do what I did here. Like, start by showing, like you could say, like, we know that this has a root at x equals negative 3, right? So we want to show that the max of that on the interval is less than or equal to 6, and then you would plug in.
I just don't know when you were explaining why you added 2.
Why I added the 2?
Yeah, on the graph.
Oh,
Like, why were we concerned about the 2?
Yeah.
X plus 3 is less than or equal to 6.
yeah, so we want to figure out for x's between negative 3 and 2, right? So really the only part of this graph we care about is like from here to here, right? And like, if you sort of have an idea of how absolute values work, you can pretty easily figure out that the value of 2 is going to be the max, right? Because if negative 3 is at 0, that's the lowest absolute value you can go, right? Can't have a negative absolute value. So the highest would have to be at 2. Now that's not always the case, right? Like there might be some case where you have something like this, right? But the maxima, and you might remember this from calculus, right? The maxima are always going to be at like the spots where the derivative is 0 or at the 2 endpoints, right? I think that's what's it called? Intermediate value theorem? No. Yeah. Yeah, either way, you know the theorem. So spots where the derivative is 0, undefined, or the two endpoints. So you just check those, invoke that theorem. And yeah, does that make sense? Yeah, good online? Hopefully. Oh, I think I have more space online, but I don't on my camera. All good, cool. All right.
I know you just said this, but what does WTS stand for again?
Want to show.
Right.
All good.
How did we show?
Sorry?
How did we show that?
So what we do is we say, I'll start up here. We say that, so figure out what the name of that theorem is. It's not intermediate value theorem. It's not mean value theorem. It's one of those annoying ones. Either way, by that theorem,
Okay.
figure out what it's called for homework. By that theorem, we know that x, absolute value of x plus 3 has possible maxes and mins at -3 and 2, because there's no like points where the derivative is 0, right? So you can say -3 plus 3 in absolute values is 0, 2 plus 3 in absolute values is 5. This is the max.
Oh, and it's always.
So then you plug this, the largest possible value, into there. And it's true that 5 times the absolute value of x minus 2 is smaller than or equal to 6 times the absolute value of x minus 2, right? If that's the biggest this could possibly be, right? It's always going to be bigger than this, or smaller, I should say. Cool. Do I want to do this one, or how are we for time? This may be a
It's a
geometric
geometric.
mean. It's a type of mean. It's sort of, so if you think about means like that you would have learned in stats, we have the arithmetic mean, which is what you're used to. This is the mean of two numbers. A plus B, you just add up the numbers, divide by the number of numbers, right? Geometric mean is similar, but it's like, so with arithmetic mean, we're using like products, or sorry, sums. With geometric mean, we're using products. So, and take this, the nth root of them. So in this case, the geometric mean is the square root of A times B. If we had 3 numbers and we wanted to take their geometric means, it would be the cube root of A, B, C. Just a different kind of mean. There's different means, yeah.
I think it's called the closed interval method.
That's what it's called, the closed interval method. Thank you.
No, don't write it out, I looked at my notes.
Closed interval methods. Cool. So yeah, try and do this proof. The arithmetic mean of a, b, both real numbers, we define that, a plus b over 2. Sorry, we got something in the chat. Fermat's theorem says if a function has a local extremum at a point where it's differentiable, then the derivative is 0. It's a local extremum. Yeah, but we're talking about some global extrema, right? So we don't care as much about local. We want like the largest, right? Because with this, we want to figure out what the largest possible value that can attain is on the interval. So yeah, and I don't know if that's actually Fermat's theorem. I don't think Fermat did stuff like that, but maybe he did. Feel free to prove me wrong. Anyways, extreme value theorem. That's what I thought it was. It's closed interval method. Yeah, closed interval method. I thought it was extreme value theorem. There's a bunch of those theorems from calculus. No problem. Easy to mix them up. Okay, so the arithmetic mean of, I already said that, the geometric mean we're given. For the geometric mean, they both have to be positive, or not negative, I should say. Because you can't take a negative square root. You can, but we're in real analysis, so you know they don't really like us doing that. We're given that A is between 0 and B, and we want to show that A is less than the geometric mean, which is less than the arithmetic mean. And we also want to show that they're equal only if A is B. I guess there's a less than B here as well. So maybe for this one, try and show it in like 3 steps, right? So try and show like that A is less than the geometric mean, then show that the geometric mean is less than the arithmetic mean, and then show that the arithmetic mean is less than B. Give that a try. I wonder if my computer's gonna work now. It might have just been like really, really dead. It probably was, because I haven't used it all year, or all summer.
You haven't opened it the past 2 weeks?
I haven't opened it in the past 2 months.
You haven't used your laptop for school?
I work from home. I'm all online, unfortunately. Maybe it is fortunate, I don't know, but I don't really like it. And it is working. It was probably just really, really, really dead. Holy cow. I'll probably get it figured out for next week, hopefully. Yeah. How's the class feeling so far?
The 3-hour lecture's honestly painful.
I bet. I would get that.
It's so hard. Even like he does give us like a 10-minute break, like it is meaningless.
Yep.
It's so rough.
So this week, or last week, sorry, you guys covered, did you just do like the absolute value stuff, the topology, like is that where you ended, was topology?
I think so.
Likely.
Metrics?
That's the absolute values of the lecture.
You did?
Yeah.
Okay, good. And then you didn't go past that, you didn't do like, what's after that? Sequences? You can't do sequences, I don't think. No. I think that's what's coming next. Sequences.
The last thing we're talking about is just open and closed intervals.
Okay, sure. There we go. Yeah, I think this computer was just super dead. I taught in the summer, but yeah,
want to show that, I wanna show A and what's it called again? Geometric mean, and then geometric mean, and.
Well, you showed this one, right?
Yeah, and then I wanna show which one?
You want to show that
Those two.
G is less than or equal to A,
And then the next.
and then, yeah. If you do them in sets like that, it's usually the easiest way. One thing you'll notice going forward in your math degree is that like, when we start proofs, we're like, you need to write this, and this, and this, and this, and then eventually it's just like, that just all goes out the window, right? We're just like, you know, this is a whole lot messier than I would have done in last semester. I'm kind of doing it on purpose because that's what you're gonna see for the rest of your math degree.
What other courses are like proofy?
What other courses are proofy? The electives, I think, are the only things left that are proofy.
In which?
Um,
Like the topics in math?
Sometimes that can be
Because they
proofy.
changed the electives that I don't have to take those anymore. Like I'm taking network science and.
Network science is proofy,
Is it?
a little bit. Probability is a bit proofy. A really proofy one is algebraic structures.
Oh.
Comp sci 2 is a bit proofy. Yeah.
Are you switching it? Okay.
When do we figure that out? So at the end of the semester.
Oh, so I did the other part of the question.
Mhm.
Why are you taking
I think
it?
this is very wrong, but I don't know.
How could you square root that?
Wait.
Travis.
Oh, I thought there was a root.
So what do you take for your math?
Okay.
Okay, can we take that up after?
Yep. Let's do it. Is Moran teaching that? Oh, great.
Oh my God, it's been 4 lectures of linear algebra again, and I want to cry about it. Yes, it's basic linear algebra.
Well, because I feel like.
Wait till comp sci 2.
I'm not taking it.
Okay, good for you.
No, I'm not touching it.
Comp sci 2 is just like,
They want me to so badly.
it's so bad. It's easy. Like it's easy, but it's like, how do you say it? Like, I remember like in the second last week, one of the students was like, something like, how do you take the determinant of a matrix? And then Moran just spent like the whole lecture explaining determinants, and it's like,
No, that's definitely like.
why is this a 400 level course? Like, you know, it shouldn't be.
Do you know why he wanted his lectures to be 3 hours?
No.
Because they were originally 2 1.5s. And then I checked my plan again like 2 weeks later and they were 3 hours for this and for comp sci 2 next semester.
No idea.
Costs can change.
Yeah,
Yeah. Well,
to some degree.
the first, like if it was just real analysis, I was like, oh, maybe it was the scheduler, but it was both of these classes, so.
That's what happened to me is I was supposed to teach late Friday night, and I had other plans late Friday night, and so I was like, I just told Mihai, I'm like, I can't do it. I'm like, if you, because that's what you can do, right? Like, it's like when you're so specialized, it's just like, well, you know, like, if like, for example, if Moran said, okay, well then I'm not teaching real analysis, like what are they gonna do, right? They kind of have to accommodate them, right? Whereas like if you were in like comp sci or something, you're a prof, they'll just get another prof to teach it, right? But it's like, well, if you say you can't teach it, then who else is gonna teach it, right?
You can teach it.
Yeah.
They should actually pay me to teach it.
If they paid me as a prof, I would teach it. Okay, let's take this up. So the arithmetic mean, the first part is to show that, like the first inequality there. Maybe I should do it over here so that online people can see. So the first step was to show that A is less than or equal to G of AB. So we know that, was it that, I think? Yep. Yep. And then, so what we can do is we can say, well, we want to show that A is less than or equal to G of AB. We know that g of ab is equal to root of ab. So that means that, how do we do this properly? Trying to think of like the best way to do this. Well,
I did it.
you squared it, but I'm sort of starting to wonder if that's a problem.
Didn't quite square it.
Sorry?
I didn't quite square it.
What'd you do?
Well, because like a squared is less than a for a less or on I think 0, 1,
Yeah.
right? I wrote it as a is less than or equal to square root of a times a, which is just equal to a.
Yep.
But then if you replace one of those a's with b,
Yep.
because b is greater,
Mhm.
that means that square root of ab is greater than or equal to square root of a times a.
It's greater than or equal to the square root of a times a.
Is that even true?
Is it true? Because what if a,
Yeah, no, that isn't necessarily true.
Is that even true?
what if that's what we have? Or maybe we'll just make it 0.2, right? Then the square root of a times a is just a, and the square root of a times b is the square root of 0.1.
Yeah,
Does that break your thing?
I think it might.
I think it does.
I think it might.
Yeah,
Wait, so why can't we do it?
we can, but I think we have to do it in like parts. So the first part is if a is, or is it if a or if b? I guess maybe there's three
B
parts.
is greater than a, so if you restrict a, you necessarily restrict b, right?
Yeah, so what if we say that that's the case? Right? So if a is actually bigger than 1. In that case, then we can square both sides. We get, which is true, right?
The mathematical definition for that is changing your goalpost.
Yeah. What if this is the case? Are we still okay? I think we are. Right? If b is still bigger than 1, then this squared is going to be less than a times b, right? And if b is bigger than 1, or I guess I should probably write this a bit more properly. If a is less than or equal to b is less than or equal to 1, so if 1's on the far side, that means a and b are both smaller than 1, then a really small number squared is going to be smaller than a small number times a big number. So I think it still works. Is that right? Yeah. So it works for all three cases. This covers every possible case. So it works always. Next. Do we want to do G is less than A?
No, I think I'm gonna do that one.
Neither do I really,
I
but we'll
got,
do.
like a little ways in, and I see something that I'm pretty sure is true, but I don't know how to actually,
Well, let's talk through it then. What do you see?
wait, never mind, I swear it again. Doesn't
Okay,
work.
sure. Well, if you're doing that, you can break it up into intervals, right?
Yeah.
But we want to show that G of AB is less than A of AB. So G is the square root of AB. this is a plus b over 2. Want to show that the square root is less than that. How are we going to do that? Well, it's tricky. Anyone see anything? What if we figure out where they're equal? How does that sound? Is okay with that? Be allowed to do that? Say we have like two functions, right? If we figure out where they're equal, even if it's multiple points, then we can figure out, like if we go a little bit to either side, we can figure out which one's bigger, right? Why don't we try that? You can square each side. Right? We have an AB here, we have a 1/2 AB. Maybe I can write that out a little bit better. It's like 1/4 A squared plus 1/2 AB plus 1/4 B squared. And I think we can subtract this to this side and multiply everything by 2, and we should get that. Is this helping us at all? I think. If we bring this to the other side, we get, and maybe multiply everything by 2, then we should get that. We can solve that. Right? Which has a double root when A equals B. Is that right? Or do I have a minus sign somewhere I'm missing? I'm missing a minus sign here. This is a minus, and then A equals B. Which incidentally proves our, the last part there, that G of AB equals A of AB, if and only if, well, at least it's one direction. You still have to show the other direction, but I think that way's a bit easier, going the other way. We good with that? So the point where G of AB equals A of AB is when A is equal to B, and the two things are the same. So if that's the case, then we can figure out what happens if A equals B plus epsilon for some small epsilon, right? What do we get? On the geometric mean side, we get square root of, if A is equal to B plus epsilon, then we get B plus epsilon times B, which is B squared plus B epsilon. And then if we take a look at A, that should be, A is B, so for B plus epsilon, which is B plus epsilon over 2. Good with that? And I think, how do we conclude that this is, it's ugly. We we might have to do another square argument there to show that this is less than this.
Is it possible to turn the camera a bit?
Yep, it sure is.
Thank you.
No problem. Is that better?
There's a message on your laptop
There's a message on my laptop,
or your iPhone.
my iPad. Device added to your account. It's probably because I haven't booted up my Mac in so long. Okay. Yeah. There we go. Yeah. Why don't we try and prove the other way for, I think there's a square argument you can make there, but why don't we try and prove the other way for that if and only if? We did one way, right? We showed that if G of AB equals A of AB, then we get A equals B. Can we show the other way? If A equals B, then G of AB equals A of AB. Let's do that. And maybe so I don't have to turn the camera again, I'll do it over here. So, suppose A equals B. Then we get that G of AB equals G of AA, which is square root of A squared, which is A. And A of AB is equal to A of AA, which is A plus A over 2, which is A. Right? So G of AB equals A of AB. And that's it. Good with that? I think that's it for time. Yeah. Pretty quick. An hour tutorials suck, but yeah.
50 minutes.
Yeah, I guess that's true. Yeah.